Hello everyone, welcome back to my channel. This is a continuation of classes on phenols. So in this session we shall learn about one important concept of the phenols, that is acidic nature of phenols. So we know that when you come to your word acid, the first and foremost thing that comes to our mind is any material that furnishes H plus ion in solution will be considered as an acid, strictly in accordance with Arrhenius theory of acids and bases. So if you come to the case of phenols, so we will be having a benzene ring, and on the benzene ring there is an attachment of OH. This is our phenol, and here you can notice OH is there. So H, so if phenol provides a free H plus ion in solution, then we can say that phenol will be an acid. In strictly speaking way, when phenol is dissolved in a suitable medium, in a suitable solvent, the H plus ion will be coming out of the phenol, creating phenoxide ion. So that we shall show over here. So when phenol undergoes dissociation, the bond between oxygen and hydrogen will get break, and that results in the formation of this one O minus with the releasing of free H plus ion. That means phenol on dissociation results in the production of phenoxide ion. Okay. So if you go with the resonating structures of phenols, you'll come to know that the lone pair of electrons that are present on the oxygen atom, we know that oxygen belongs to group number 16. There will be a total of 6 valence electrons, but among 6 valence electrons, only 2 valence electrons will take part in bonding, as you have observing over here. So oxygen having 1, 2, 3, 4, 5 and 6 valence electrons are there. Among the 6, 2 electrons were involved in bonding, and remaining 4 electrons will remain as lone pair of electrons. So the lone pair of electrons present on the oxygen atom will take delocalization, will get delocalized with the pi electron density present in the benzene ring, that we can show like this: 1, 2, 3. There are 3 pi bonds within the benzene ring, and those 3 pi bonds will involve in delocalization with the lone pair of electrons present on the oxygen atom. So because of this delocalization, we will be observing resonance in phenol, and because of the resonance there occurs development of free H plus ion. How? That we shall observe by writing the resonating structures for phenol. So firstly, this phenol OH, this lone pair of electrons will shift over here. So to balance the valency, the pi electron density will shift on to the adjacent carbon atom, creating one canonical form. And in this canonical form, there will be a negative charge over here, double bond OH, and one lone pair. But here one lone pair of electron shifted and distributed between carbon and oxygen, so that we got a double bond, and due to loss of lone pair, oxygen will attain positive charge by keeping these 2 pi bonds as it is. And now the carbon will not remain with negative charge on it. This negative charge will get redistributed between these 2 carbon atom, and this pi electron density will shift to adjacent carbon atom, creating one more canonical form. And in this, the negative charge will develop over here, and because of distribution of the negative charge, there develops a new pi bond, and this pi bond remains as it is, double bond OH with a positive charge on oxygen. And now this negative charge will distribute here, so that this pi electron density will move on to the adjacent carbon atom, creating one more canonical form. So here there will be a negative charge, new pi bond, here one new pi bond, double bond OH with a positive charge. And now this negative charge will shift over here, and now to balance this movement, the H will come out and this electrons will once again shift on to oxygen. So that we'll be getting a canonical form like this, O with negative charge. Because we have one lone pair of electron as it is, due to shift of this pi electron density onto oxygen, there occurs excess of electron density, and so that H is coming out as H plus by creating phenoxide ion. And if you observe, compare it to phenol, in phenoxide ion, here we have a negative charge, and this negative charge is more pronouncedly will get dispersed in the benzene ring so as to make it stable compared to phenol. That means, compared to phenol, both phenol as well as phenoxide, both will undergo resonance, but compared to phenol, phenoxide ion is more resonance stabilized because the negative charge present on the oxygen atom will be more dispersed, more delocalized with the pi electron density of the benzene ring, so that phenoxide ion is more stable compared to dispersion of a lone pair of electrons present on the oxygen atom with pi electron density of the benzene ring to create the resonance. That means phenol and phenoxide ion both will undergo resonance, but in comparison, phenol is less resonance stabilized compared to phenoxide ion. So, compared to phenol, phenoxide ion is more stable. So, to become phenoxide, phenol will easily eliminate the H to produce H plus ion. So, any material, if it is donating, if it is creating a H plus ion in solution, obviously we used to call the material as acid. So, we can say phenol is acidic in nature. Phenol is acidic. Okay, and phenols are having a degree of dissociation or dissociation constant, that is Ka. The order of dissociation constant of phenols is of the order of 10 to the power of minus 10. So, this is the order of phenols. If you go with a normal phenol, just you go with a simple phenol, not with any isomeric one like a cresols or substituted phenols, the Ka value for a simple phenol is around 1.3 into 10 to the power of minus 10. This is the actual Ka value for phenol. We know that if a material is having greater value of Ka compared to others, then that material is more acidic compared to the other one. I repeat, a material with greater value of Ka, that is dissociation constant compared to other materials, then the one with the greater value of dissociation constant will be considered as stronger acid. So, as a whole we can say, due to resonance, phenol can readily produce phenoxide ion by producing H plus. So, due to development of free H plus ion by phenol, phenols are considered as acids, and phenol is having a degree of dissociation constant of 1.3 into 10 to the power of minus 10. And we can do a comparative study of acidic strength of phenols with other functional groups such as alcohols, which are also considered as acids, along with carboxylic acid, in a strictly speaking way monocarboxylic acids. So, we can do a comparative study of acidic strength of phenols with both alcohols as well as monocarboxylic acid. And now we shall proceed to the same and shall do the discussion with respect to the comparative study of acidic strength of phenols with alcohols in case 1 and monocarboxylic acids in case 2, and there we shall understand which are all the factors that influences the acidic strength of a material, and there itself we shall see the variation in acidic strength based on their dissociation constant values. In comparative study of acidic strength of phenol with respect to other functional groups, firstly we shall consider comparison of acidic strength between alcohol and phenol. So we know that both alcohol and phenol both are acidic materials only, but between alcohol and phenol which one is more acidic and which one is less acidic with respect to their acidic strength, that we shall discuss now. So alcohols can be simply written as ROH, and if the H plus ion is eliminated from alcohol, if H plus is eliminated, we are going to get RO minus plus H plus. So alcohol on dissociation results in the formation of alkoxide ion with the expulsion of H plus ion. And if you go with the phenols, which we already written, so if you consider phenol, here we are having R, here R in the sense it can be an alkyl group, but here in case of phenols we are having a benzene ring. So when phenols, when H plus ion got eliminated from phenol, we are going to get O minus, that is phenoxide ion with the expulsion of H plus. So phenol will produce phenoxide ion. So here I have written the dissociation reactions of both alcohol and phenol, and here you can notice in case of alcohol we are observing the elimination of H plus ion or production of H plus ion, and a similar thing we are observing with respect to phenol also. But comparatively phenols are more acidic in comparison with alcohols. Why? The answer for this question is, you can notice over here, in case of alcohol this R group will be an alkyl group. So when you are having an alkyl group, in case of alkoxide ion we cannot expect the dispersion of negative charge present on the oxygen atom, because we have an alkyl group, we cannot expect resonance over here. But if you come to the case of phenol, here we are having a benzene ring consisting of 3 pi bonds, and this negative charge can get easily dispersed, can undergo delocalization so as to produce resonance. So if the material is involved in resonance, then that will become more stable in comparison with the other material which is unable to undergo resonance. So we can say that there is no resonance in alkoxide ion, but there is a resonance in case of phenoxide ion. So phenoxide ion is more resonance stabilized compared to alkoxide ion. So due to resonance stabilization, phenoxide ion is more stable compared to alkoxide ion, in the sense formation of phenoxide ion will occur more fastly compared to formation of alkoxide ion from alcohol. We know that if a material furnishes H plus ion in a more faster way compared to other, then we consider that material as a stronger acid to compare it to other. Compared to other, if an acid furnishes H plus ion relatively slowly, then we cannot say that acid as a stronger acid, right? So the one which produces free H plus ion more fastly compared to other, that will be considered as a stronger acid compared to other. So here the formation of phenoxide ion will occur more fastly compared to alkoxide ion, and phenoxide ion is more stable compared to phenol as well. Alkoxide ion is less stable compared to phenoxide ion. This is with respect to resonance. But with respect to other factor also we can explain why phenoxide ion is more stable and why alkoxide ion is less stable, and why the formation of H plus is relatively slow in case of alcohol and formation of H plus ion is more fast in case of phenol. If you notice, here I have written R in the sense alkyl group. We know that all the alkyl groups are electron donating in nature, right? So all the alkyl groups are electron donating in nature. And if you come with the phenol group, that is benzene, that is a phenyl group, and the benzene ring is an example for electron withdrawing group. So here also we are having a difference between alkyl group and the benzene ring that is present in case of phenol. So here the alkyl group is electron donating in nature. So electron donating alkyl group will donate electron density to oxygen through positive inductive effect. So here the electron density is moving towards oxygen atom from the substituent. So here we are observing plus I effect. And here in case of phenol, the benzene ring is an electron withdrawing group. The electron density will be pulled from oxygen atom towards the carbon atom. And in case of phenol, when the electron density is pulling more towards the benzene ring, there occurs decrease in the electron density on oxygen atom, so that the bond pair of electrons present between oxygen and hydrogen will be shifted towards the oxygen more fastly, and that makes the elimination of H as H plus in a more easier way in comparison with alcohol. So here we are observing minus I effect. So because of minus I effect, elimination of H plus is more faster in case of phenol in comparison with alcohol. So with respect to all these things, we can say alcohols are less acidic in comparison with phenols, and the justification for this statement can be given based on the dissociation constant values. The Ka value for alcohols is of the order of 10 to the power of minus 16 to 10 to the power of minus 18. But we have given the dissociation constant values for phenols in the previous minute, that is of the order of 10 to the power of minus 10. We said that in comparison with any two materials, when you are telling about acidic strength, the one with the higher value of dissociation constant will be the stronger acid compared to the other which is having relatively lower value of dissociation constant. So based on all these factors, we can say that phenols are more acidic than alcohols. This is the conclusion we can draw by the discussion what we made under the comparison of acidic strength between alcohol and phenol. And now we shall observe the comparison of acidic strength between phenol with that of monocarboxylic acids. Now we shall see the comparison of acidic strength between phenol with monocarboxylic acids. So phenol, as we already written, phenol having a benzene ring with the 3 pi bonds OH. So this phenol will reversibly undergo dissociation so as to produce phenoxide ion O minus plus H plus. But if you go with phenol, will gives phenoxide ion. But if you go with the monocarboxylic acid or C double bond OH, if you go with monocarboxylic acid, these with expulsion of H as H plus, we are going to get R C double bond O minus with expulsion of H plus. So carboxylic acid on dissociation results in the formation of carboxylate ion. So now we shall do the comparison of acidic strength between phenols and that of carboxylic acid in a strictly speaking way, monocarboxylic acid. So here you just notice, here also we are having negative charge on oxygen atom, and here also we are having negative charge on oxygen atom, provided in both the cases resonance is possible. In previous case, that is between alcohol and monocarboxylic acid, the resonance is possible only with phenol but not with alcohol. But between phenol and monocarboxylic acid, upon their dissociation, whatever the ionic form we got, that is phenoxide ion and carboxylate ion, in both the cases resonance is possible. Then how to predict which one is more stable and which one is less stable, so that to say which one can produce H plus ion more fastly compared to the other? The answer for this question is carboxylate ion will form more fastly in comparison with phenol or phenoxide ion. The reason for this is, you can notice, in case of phenoxide ion, the negative charge which is there on the oxygen atom has to disperse between oxygen and the carbon atom of the benzene ring. But if you come to the case of carboxylate ion, the negative charge will distribute between two electronegative oxygen atom. So because of this shift, you will be getting the structure in this way, CO minus double bond O. And for these two forms, we can write a resonance hybrid as RCOO. So there will be a total dispersion of the negative charge between these two oxygen atom. Here also we get negative charge, and here also we will get negative charge. So this is the resonance hybrid of these two canonical form. So because of dispersion of the negative charge between two electronegative oxygen atom, the expulsion of H plus ion from carboxylic acid from monocarboxylic acid is more faster compared to production of H plus ion from phenol, wherein the formed phenoxide ion will make the dispersion of negative charge between electronegative oxygen atom and less electronegative carbon atom. And based on the dissociation constant values also, we can observe that the dissociation constant of the phenol is of the order of 10 to the power of minus 10, but for monocarboxylic acid, the dissociation constant value is of the order of 10 to the power of minus 5. We said that compared to the other, the one with a greater value of dissociation constant will be the stronger acid compared to the other. So based on all this, we can say that compared to phenol, carboxylic acid is more stronger. The acidic strength of monocarboxylic acids is very much high in comparison with phenol. And this is the comparative study of acidic strength of phenol with that of alcohol and monocarboxylic acids. In our next session, we shall discuss what is the effect of substitution on the benzene ring with respect to the acidic strength of phenols.